Okay, so this is our extra lecture to account for the fact that Monday is Labor Day. And in this lecture, we'll be finishing up chapter 18 so that we can start fresh with chapter 19 on Tuesday. So chapter 18 is all about wave optics, which means that our optical instruments are similar in size to the wavelength of the light that we're interested in. Whereas ray optics is looking at larger optical devices. So something like the lens on my glasses would be a case where we would use ray optics, which will be the topic of chapter 19. But for the moment, we need to finish up chapter 18 so that you can learn this really important material, approach the problems that have now been shifted to the last homework, and do well on the final. So with that out of the way, I'll go ahead and start my screen share. And actually, I have to leave it like this, unfortunately. But okay, so we left off by looking at thin films, which are effectively optical devices, wave optical devices, where you have one reflection off of the top surface and another reflection off of the bottom surface of the film. And so as we saw, there are a couple of equations, and in some cases, one of these equations will be constructive and the other destructive, and in other circumstances, they will be flipped. And in order to figure out which case we're in, we have to ask ourselves, how many reflective phase shifts are there? So like I said, one ray of light or wave of light will reflect off the top of the film, the other off the bottom. And by going back to slide 6 and comparing the indices of refraction on the left and right of that boundary, we can determine if the reflected wave has a phase shift. And so if there's a phase shift on the front and the back, then we use this set of equations, the first being constructive, the second being destructive. Or if there's no phase shift on the front and the back, we use them the same way, but we flip the use of them if only one side has a phase shift. So go back and watch the previous video if that's something that's confusing for you. But we'll now go ahead and move on to section 18.3, which is on double slits. And we actually will also cover what happens if you have a single slit. But let me walk you through some important details on our assumptions when we're doing this physical analysis. So when we're analyzing these double slits, we have to assume that the slits themselves are really, really small. So this is actually a picture of a set of double slits that you can buy on Amazon for like $10. And you can see that in each of these, so there are 4 pairs of slits here, right? So there's a total of 8 openings in this film, but there are 4 double slit, optical objects. So you would only shine your light on one of these at a time. For example, you could shine your laser beam right here, and there are 2 openings there. When we're making these double slits and analyzing them, we're going to assume that the openings, so the openings of the slits, are really small. So really small, so small that the light passing through them is basically collimated, like it's not a wide array of light traveling through the openings, but that the separation between the slits, so the separation between the 2 openings, that this separation, and let me just check what the formulas call it a little bit later, they call it lowercase d. So this separation, lowercase d, is about the size of the wavelengths. So it can be a little bigger or a little smaller. And that's actually what these labels are down here. So this first pair, this first double slit, has a spacing, so a gap between the 2 openings of 1/4 of a millimeter, 0.25. Whereas the one on the far right, that spacing is a millimeter. And so these are kind of the sizes of like your pencil lead, if you have a mechanical pencil, somewhere in that range. And that's typical for an optical double slit, something around 1/10 of a millimeter. Okay, so now we can ask ourselves what actually happens when we shine light, for example, a laser beam, although it can be any kind of light, we just need to focus it, through these double slits. And so what happens is when the wave goes through these double slits, it diffracts, right? So diffraction is this process where a wave, when it goes through an opening of a similar size to its wavelength, the wave will kind of spread out on the other side. So it's able to go places that we wouldn't expect it to go if the wave were made up of particles, right? If you throw baseballs through a doorway, the baseballs will only ever hit directly behind the doorway. But if you speak through a doorway, the sound will kind of travel outward a little bit, even without taking into account reflections. So that's what's happening in each of these openings. And then these two wavefronts, the one from the left slit, the one from the right slit, are overlapping, very, very similar to what we saw in chapter 17 with that two-dimensional circular wave interference patterns. And so what we do then is we project this onto a wall. So it's like kind of the most, maybe one of the more boring videos that you could watch, like with your projector. You could take your projector and put a double slit in front of it and then project that onto a screen. And that's this thing labeled a viewing screen here. But what you see is really magical. So like I said, if this were just throwing baseballs through two openings, you would expect to just see a bright spot behind the left slit and a bright spot behind the right slit. But what we actually see is we see a whole bunch of alternating bright spots and dark spots. And that's coming from the different points of interference along some line in the circular wavefront. Some places will have constructive interference, that's where we get a bright spot, and other places will have destructive interference, that's where we get a dark spot. And so this works for any sort of wave, but we can see it here in particular for light. That's kind of what we're focused on in chapter 18. But you can also make a sound double slit. You could do this with ocean waves just by putting some rocks in the water as the waves pass by. And you can even do this with subatomic particles because of quantum mechanics. They actually also act like waves, which is something you'll learn more about in 3C. And so we can do a double slit with single particles if they're very small quantum things. But anyways, so then we can ask ourselves, a very physicsy question of sort of, okay, I see this pattern, but how do I describe it in the language of math, right? That's kind of what we've been doing throughout this class is noticing patterns in nature and asking, how do I describe this with math? So the first thing we want to do is we want to just draw a slightly better picture here. So you can see we have our waves with a wavelength lambda that are being shown onto this double slit. We say that they're incident onto the slit, just meaning that we shine the laser onto it. And then they travel through these tiny, tiny openings that are separated by a distance d. So this distance right here is what we call lowercase d. And that's basically all that you need to know about the double slit in order to be able to start to describe what this pattern should look like. You just need to know that separation of the slits, and you need to know what color of light you're shining. So you need to know the wavelength lambda. And then what you can see is that the line directly horizontal from the middle of the two slits, we get constructive interference there. You can see how these wavefronts, the peaks are overlapping at all these points along this line. And so we get what's called the central maximum. And this will generally be the brightest spot on that screen that we're projecting the image on. And then on either side of that, we get a dark spot. You can see that's where we have a node, right, where we have destructive interference. And then on either side, again, we get an antinode. So for those situations, these are the first order maxima. So M is 1 here. And we have a second order maxima farther away. So we just keep on increasing this variable M, and we march farther and farther away from the center. Okay, so this is a better picture, but now let's look even more carefully at what's happening. So we have a double slit, and you can see that from far away, we can just imagine that the light is traveling along this purple line to some point on the screen. Okay, and we can draw a right triangle here. So we have this right triangle, and the angle from the double slit to the point of interest we call theta. And then on the bottom here, this is what we call L. They label it down here on the diagram. That's basically how far is your double slit from the screen or the wall or whatever that you're projecting this image on. Okay, so if I shine my laser through a double slit and I'm a meter away from the wall that I'm going to project the image on, then capital L would be 1 meter. And generally, capital L will be quite big. You can see in this picture, they say usually capital L will be much, much bigger than this little d, the spacing between the slits. And that's why we can measure this angle theta as just coming from the double slits, right? We don't really say which of the two. It's just because L is so big that it doesn't really matter when we're labeling these things. And so then this vertical distance, which we often call delta y, which tells you basically how, if we have our double slits oriented where one's on top of the other, then delta y will be how much higher on the wall, if I get my ruler out, how much higher on the wall, this point P is compared to the center line. And we can just do some basic, this is a right triangle, so we can do some basic trig and see that this is just L tan theta. And when we zoom in to the double slit, we can see that the reason that the interference is happening is that if you're on a point above the horizontal, the light from the bottom slit has to travel a little bit farther, this extra tiny distance compared to the light on the top slit. And so this tiny distance delta r is just equal to d sine theta. We can do some triangle, geometrical identities here to find that this theta is the same as this theta. These two angles are identical. So on the blue triangle versus on this right triangle from earlier. And you have to be careful about this. The book is a little weird with it, but for very small thetas, so for theta very small, there's a really nice property, a really nice assumption we can make, which is that for very small theta, theta is approximately equal to sine theta, which is approximately equal to tan theta. And this is assuming that theta is being measured in radians. With degrees, everything gets a little bit more annoying. So if you're measuring your angle in radians, and your angle is really, really small, then sine theta and tan theta and theta, they're all basically the same number. And this is what we do in section 18.3 to really simplify our formulas. In section 18.4, which we're going to get to soon, they don't make this assumption. I don't know why. I think it's fine to do there as well, but we should stick with the formulas in the book. So if you see double slit formulas, just use the ones that I'm going to have in the presentation from the book that are assuming that theta is very small. Whereas in section 18.4, which is on diffraction gratings that we're about to get to, they, for some reason, don't make this theta small approximation. So we should just use the formulas that they use so that you make sure to get the right answers on the homework and everything else. But in reality, we can often assume theta is quite small. And the reason is that usually this double slit is far away from the wall that it's projecting on. So we have a triangle that's really stretched out horizontally, which means that that angle will be close to 0 radians. So anyways, I say all of this basically to say that, this delta r, we're trying to find out a phase difference. So if we go back to our delta phi is, 2 pi delta x over lambda, remember what this told us was that for constructive interference, we want our delta x to be some multiple of lambda. And so we can just say, if we want our delta r to cause constructive interference, to cause there to be a bright spot, that we can just set this path difference, this delta r, equal to some integer times lambda. And then if we assume that our angle theta is very small, then this just becomes d theta equals m lambda. And we can just rearrange that to solve for theta to figure out what angles theta tilted from the horizontal would cause this there to be a bright spot located on the screen there. And these angles are just m lambda over d. So this is where it's coming from. It's coming from what we learned in chapter 17 on how to find this phase difference for interference problems. But you can see we list this formula here now for you in a nice typeset way, that these theta m, so the values of theta above the horizontal, where we get bright spots, so constructive interference, are just m lambda over d. And m can be 0 here because that would just be an angle of 0, which would give us this central maximum, right? When m is 0, where the central maximum, if m is 1, just to draw this on the diagram, then we would have, let me try to draw that a little bit better. We would have this right triangle right here. And so this angle on the left is our theta sub 1, just to give you a practical example of what these thetas are telling you. So to find the theta where you get a bright spot, we just have some integer times lambda over d, where d is how far apart those two diffraction grading, or sorry, how far apart those two slits are. Right, so going back to this picture, for the rightmost double slit, that little d value would be 1 millimeter. And then our lambda would depend on what color light. So if we're shining a red laser, that would have some wavelength associated with it, a few hundred nanometers. Whereas if we're shining a blue laser, it would be a slightly different lambda. So in effect, what we'll see in a minute is that different colors, the bright and dark spots are at slightly different positions, which is very useful to chemists because it allows them to find what light is composing some sample. And if you've taken a chemistry class, you may have like heated elements in a flame and saw they were different colors. So if you want to precisely figure out what color that is, you can actually use something like a double slit, which is very, very handy. So anyways, so then what we can do is we can use the fact that for small theta, the angle is basically equal to sine theta, which is basically the same also as tan theta, as long as we're using radians. And so if we want to figure out how high up, so if we want to figure out this y value, how high up is the nth maximum, then all we have to do is say we have the theta, so we have a right triangle, we have this theta, and so this height here will just be L tan theta, but since our angle is small, this is just L times theta. So to get our y value, we just do L times theta m, and you can see that's what this formula is down here. We've just taken this theta m formula, m lambda over d, and multiplied it by capital L, the distance from the double slit to the screen we're projecting it on. So it's m lambda capital L over d. That's the only difference. So you can see we're assuming in both of these equations that the angle theta is very small in order to use our approximation. So at the end of the day, we can find the positions of these bright spots using this formula, this nice formula here. Okay, so let's do a practice problem so you can actually get a feeling for this. So we have light from a helium neon laser, which will be some color, so 633 nanometers. It illuminates two slits, so hey, we've got a double slit, that are spaced 0.4 millimeters apart. So they've already told us a couple of important facts. Our lambda is 633 nanometers. So we can write that as 633 times 10 to the minus 9 meters. And our little d, the spacing between the two slits, is 0.4 millimeters. So we write 0.4 times 10 to the negative 3 meters. So that's taking care of our conversions. And we see a bright fringe at a point 9.5 millimeters from the center of the screen. So our y sub m, where we see a bright spot, is a distance 9.5 times 10 to the minus 3 meters from the center. So you see how this y sub m is a physical distance. That's why I used that formula rather than the angular formula, which is what we would want to use if they told us some value in radians or degrees. And if it were in degrees, we would need to convert that to radians for it to work. So throughout chapter 18, you want to be trying to work with radians, which it was also true in the earlier chapters as well. Okay, And so then they want to know what is M and how much farther does the wave from one slit travel at this point than the wave from the other slit. So they're asking us to find what M is for this particular bright spot, and also to find that delta R that we were referencing earlier. So how much farther did one beam of light travel than the other beam of light? Okay, so to get our M, this is a straightforward application of our equation. So we have the equation y equals m lambda L over d. Oh, sorry, they also told us L here, which is 2 meters. Somehow skipped over that. So then y is m lambda L over d. So we can rearrange that, and we find that m is yd over lambda L. And just plugging in our values to a calculator, which I've done myself here, get a value of 3, which is good. M should be an integer, so if it's not, you probably rounded something a little incorrectly, or maybe you've used the wrong formula. So checking that your fringe number is an integer is a good way to sanity check yourself. So that's telling us that we're up here at M equals 3. So this is the one, this is the bright spot that we're looking at, apparently. Okay, so then how do we find delta R? Well, that formula is not on slide 14, but if we go back to this slide, I show you that delta R, which is d sine theta, we know that for constructive interference, it has to be m times lambda. So we can actually do it that way as a shortcut, or we could find theta using our formula and then do d sine theta or just d theta. We would also get delta R. So there are a couple of options, but since this is a constructive interference point, I'll just go ahead and use the easiest formula, which is just m times lambda. And so all we have to do to get our delta R is m times lambda, which is just 3 times this 633 nanometers. And so we get a really small value, 1.9 times 10 to the negative 6 meters. So, this is on the scale of micrometers, right? Like similar to microorganisms. And so it's a very small difference in travel length. But, it's on the scale of the wavelength of light. And that's why we only see this double slit behavior when that spacing little d is not too much bigger than the spacing of the wavelength. So you can see here that this wavelength is like almost 10 to the minus 6 size, and this spacing d is like 10 to the minus 4. So they're still a factor of 100 different roughly, but that's close enough for the double slit's interference pattern to be visible. Okay, but if we tried to shine a laser through 2 doorways that were separated by a few centimeters, that wouldn't work. We wouldn't see any interference pattern visually, at least. Okay, so now moving on from our example, there are a few more formulas that we can use to characterize the double slit. So a direct consequence of formula 18.8, since m can only be an integer, we can immediately see that these bright spots are spaced out by lambda L over d. So you can see this is labeled on the diagram, but just to label it again for you. So the spacing in between like bright spot 2 and 3, for example, we can call this delta y. And for any 2 bright spots that are adjacent to one another, that spacing will always be lambda L over d. And this is just coming from that previous equation, and considering the fact that m is always an integer, we have to have the same spacing between each pair of bright spots. And then similarly, because in the double slit, everything's nice and symmetrical, the dark spots are just m plus 1/2 times lambda L over d. So all these formulas for position of the spots, either the bright spots or the dark spots or this gap between them, they all have these lambda L over D factors in them. That's the critical thing. That gets your units to be right. Everything works out. That has units of length. But then you can see when we're finding the bright spots that they occur at every M value, so 0, 1, 2, 3, so on. And when we're finding the dark spots, they occur at every M plus 1/2. So the first one is at 1/2 lambda L over D. That would be this dark spot 1 here on the diagram. So the one right above the 0, the central maximum. And we could also have any other M value to find any higher order dark spot, which are also called dark fringes. And the spacing between any two bright spots will be lambda L over D, and the same is the spacing between any two dark spots. You can see, because M is an integer, the dark spots that are adjacent to one another are also separated by a distance, lambda L over D. Okay, so we can do another problem just to really drive this home using that information. So we have a double slit interference pattern is observed on a screen 1 meter away. So they immediately tell us that L is 1 meter. The two slits are spaced 0.3 millimeters apart. So the little d is 0.3 times 10 to the minus 3 meters. From the center of one fringe to the center of the 9th bright fringe from this one is 1.6 centimeters. What is the wavelength of light? So they tell us that some sort of delta y, so we have to be careful what particularly they're saying about delta y here, but something related to delta y, I'll put a little question mark delta y here, is 1.6 centimeters. So 1.6 times 10 to the negative 2 meters. Okay, so now we have to ask ourselves, what is this spacing? Is it really delta y or is it something else? And so we have to read this carefully. Let's read it again. So from the center of one particular fringe to the center of the 9th bright fringe from this one. So it's 9 bright fringes away. So maybe the first fringe is the 3rd one, and then the next fringe that we see is the 3 plus 9, so the 12th fringe. So they don't tell us the numbers of the particular ones. They don't tell us any M values, but they tell us that the difference between the M values is 9. So what that means is that this isn't delta y, this is 9 delta y's, because these two fringes, these two interference spots are 9 steps away from one another. Okay, so to get delta y, what we need to do is we need to take 1.6 times 10 to the minus 2 meters and divide it by 9. Okay, and so when I do that, I got 1.78 times 10 to the minus 3 meters. And now we can get lambda quite easily, right? We have a formula, delta y is lambda L over D, so we can just rearrange that. So delta y is lambda L over D. We want to find the wavelength of the light. So this is saying that delta y times D over L is lambda. And now plugging that in, when I solve, I get 530 nanometers, which is just 5.3 times 10 to the minus 7 meters. It's just for light, we often like to talk in terms of nanometers. So you may have to do these sorts of conversions on problems on the homework or on quizzes or the final and so on. So this is our light. And this is in the visible part of the spectrum. This is maybe greenish colored somewhere around there. And so that's also a good sanity check. Are you getting something, if you're expecting visible light, are you getting something in that range, like from 400 to 700 nanometers or so? And since they say we can see the fringes, we can expect it to be visible light. We can, of course, do interference with any type of wave. Even if we can't see it, we would just need some sort of sensor to pick up where the bright and dark spots are, right? So even a wavelength like X-rays that we can't see, as we'll discuss later, we could put a little photographic plate there, and it would become, bright on the parts where the X-rays can pass through and dark on the parts where the X-rays can't pass through. or where the X-rays are destructively interfering, I should say here. So anyways, this is how we get the wavelength. And you can see the beauty of this delta Y formula is that in reality, when you're looking at one of these images, so you're looking on the wall, it can be hard to tell which one is the center one, right? Just practically speaking, it's hard if it's not labeled to tell that this is the center one. But what you can do is you can just say, well, here's 1, here's 2, here's 3, here's, so I can say, well, from this one to this one, this is going to be 3 delta Y. And so then you can get delta Y and you can find the wavelength, or you can find the spacing of the slits, whatever you don't know in the problem, you can find it this way. So it's a really handy trick. And the reason that we often do multiple delta Y, so here we have a spacing of 9 delta Y, is that that minimizes the error, right? When we measure this 1.6 centimeters, that's easier to measure than if we just tried to measure just 1 delta Y, which would be, maybe, as you can see, quite small. So on the scale of millimeters, like slightly below 2 millimeters. So it's beneficial if you're in real life trying to do an experiment with interference patterns to just find the spacing, the delta Y, for a large gap. So for 9 brightness fringes or something like that, so that you minimize your error and you have something that you can measure with a ruler instead of with some micrometers or something. Okay, so this is what you really need to know about double slits, but the next section, 18.4, will be very, very similar. Okay, so here we're talking about diffraction gratings. And the idea behind a diffraction grating is maybe the question that you were wondering when you were listening to me a moment ago. So I was saying all this stuff about 2 slits, and so a good question to ask yourself is, okay, what if I had 3? Or what if I had 4? Or what if I had 1,000? So you can see the types of questions physicists tend to naturally gravitate towards. And so that's what diffraction gratings are. Diffraction gratings are what happens when you take a double slit and instead of 2 openings, you have 1,000 openings or something crazier. And so this picture, again, I just got off AliExpress or something. You can buy these for very cheap. You might have even seen them in glasses if you were a kid and had those rainbow glasses that make everything look rainbowy. Those are just very cheap diffraction gratings. And so the way you make them is you just cut a bunch of tiny openings next to each other in some material so that the light can travel through it. You can have a piece of glass that you coat in like paint or something, and then you scratch off the paint to make the openings. So that's a practical way you can make these. And as we'll see in a little bit, there's another way to make diffraction gratings that's a little bit trickier, but that is relevant for a lot of applications. And so in this picture, this is just the picture of some particular diffraction grating, but you can see that the company sells them with different numbers of lines, like per millimeter. So 300 lines per millimeter, 500 lines per millimeter, and so on. And so depending on how big of a chunk you have, like maybe this chunk is 5 millimeters, you would multiply the line value by 5 to get the actual number of openings in this diffraction grating. So let's look at a picture of one of these, right? It looks atrocious. So you have a ton of openings. The waves are traveling out from each of them and interfering with one another. So it's for every opening, you have a different circular wave coming out, and they're all interfering. But it turns out that these are really symmetrical. You can see that the delta R for each one compared to the next one is just d sine theta, the same as with the double slit. So the formula that we get is basically the same formula as a double slit. Remember, for the double slit, we said that theta was really small, so that we could say that sine of theta was approximately theta, which was approximately tan of theta. And so in the diffraction grating formula, if you put a theta where the sine of theta is, you'll get the same formula as the double slit, just m lambda over d. And if you put a theta where the tan theta is, you'll get the same formula for the position of the bright fringes. So it's really, really the same formula. I don't know why they leave the sines and tangents in the diffraction grating section. I guess that's telling me that they're considering the case where you might have a diffraction grating really close to something that you're measuring the position on, which can happen in equipment, like if you have a spectrometer that uses a diffraction grating, which we'll talk about in a moment. you can have the case where theta isn't small. So fair enough, book. I can see why you have a different formula here, but I just want to emphasize that it's the exact same formula, essentially, as the double slit experiment. It's just that here they're not assuming that the angle theta is small. So we could have a larger theta, like, pi over 4 radians, versus for the other formulas for the double slit, we have to only take theta to be very small, like pi over 20 radians or something. So anyways, in this case then, if we want to find the angle theta, we have to say that it's sine inverse of m lambda over d. And be careful that your calculator is in radians mode when you're doing this so that you get radian angles out. And then we can plug that into the lower equation and get that the y position of the nth bright spot, the nth bright fringe, is just L times tan of sine inverse of m lambda over d. So you can see it's a little messy. There is a way to simplify this, but I'm not going to do it because you shouldn't have too many problems that you have to use this for. So just plug in your m, lambda, and d, take the inverse sine of them, take the tangent of whatever your calculator spits out for that, multiply it by L, which is how far away the diffraction grating is from what you're projecting the interference pattern on. And by doing all of that, you'll get the position of these bright spots, right? So the vertical position here, this is that y sub m, and then the angle here, you can see they label theta 2. This is the angle to get up to the second bright spot here from the horizontal. Okay, so I've said a lot of words, but we've got to say a few more things about diffraction grating. So they're almost exactly the same as double slits, but of course we have more openings, right? So that has to do something. So it doesn't change the position of the bright and dark spots, it turns out. It leaves the position the same. But what it does change is it changes how narrow and how bright those spots are. So the picture on the left here, this is when n equals 2. So that's just a double slit. That's what we were covering a minute ago in section 18.3. And you can see that these bright and dark spots are kind of fuzzy, and the amount of light, so the fuzziness is telling you that it's kind of spread out over a bigger area. And then the total amount of light, they're kind of dim. They're not particularly bright. And so what happens when we have more and more openings, so a diffraction grating with a larger and larger n, is that the intensity, so the brightness of those bright spots increases, and it actually increases like n squared. So if we have twice as many openings, we'll have twice as bright of spots, but the trade-off is that those spots get thinner and thinner. And for a lot of applications, that's actually really good. So we'll see in a minute that oftentimes we really want very, very thin, but exceedingly bright, bright spots. Because that way, if we have lots of colors, the bright spots for the different colors won't overlap. And we can actually tell exactly which color each of those spots is, because we can use our formulas to find the wavelength. And so this is actually one way that scientists characterize a color. Like, if you or I see a color in everyday life, like these purple flowers behind me, I might say, oh, that's purple or that's violet, right? It's hard to describe exactly what color that is. But as a scientist, what you can do is you can take that light and shine it through a diffraction grating with a lot of openings, so a large n value. And that light will very precisely create bright and dark spots. And if we have lots of openings, those bright spots will be very narrow. And so by measuring that position, I can tell you exactly what color it is, right? I can tell you the wavelength is, I don't know, 200 nanometers or something. And if it's multiple colors that are creating that, then I can tell you exactly which colors, right? So if we look at the sun, there are lots of colors coming from the sun, and I can tell you exactly which colors they are. And by doing that, we can plot like a black body spectrum like we saw in chapter 12, or we can figure out which atomic transitions are occurring, which is something you'll learn more about in WC or in your chemistry classes. Okay, so let me show you how we do that. So just like I was describing, we let some light in, we reflect it off of a mirror just to focus it. That's what this collimating mirror does. And then we shine it through a diffraction grating. The picture labels it as a transmission grating. So this is one where we just have a bunch of little tiny openings that are all next to each other. And that will cause the bright and dark fringes to appear. And if we just zoom in on one of these regions, then we'll be able to see how those different colors slightly separate, right? Different wavelengths. You can see if lambda is bigger, then that'll cause that sine theta to be a little bit bigger. So the bigger the wavelength, the more red it is, the slightly farther away that color will appear. And by just looking at one set of those bright spots, we can get the spectrum. And so you can see if we do that for sodium, so if you heat up sodium and you say, what colors is it making? You can see it's actually making a bunch, right? Some blue, some purple, but the most prominent ones are these two yellow ones. And so if you ever see these yellow tinged street lamps, those actually work by exciting sodium atoms in a complex process. And so they have a kind of yellowish tinge to them. And that's coming from the fact that certain orbitals, the energy difference between them corresponds to a photon with yellow light. But you can observe that by using a diffraction grating. And so this whole apparatus is known as a spectrometer. So it's a tool that we can use to tell not only what colors something is emitting, but we can take that information and use some quantum physics and stuff to figure out which elements are inside of that thing. Or if it's a black body, we can tell what temperature it's at, right, by looking at the spectrum. So that's one way we measure the temperature of the surface of the sun, for example, by looking at the spectrum from the sun and matching it to some black body spectrum like we saw in chapter 12. Okay, so we can also, instead of having openings, we can, by putting a bunch of little cuts, little indentations in a mirror, we can also separate the light and make a diffraction grating. So I just want to put that in here. Sometimes people call these reflection gratings, whereas the ones we were talking about earlier, where you have openings, these are known as transmission gratings. But they work exactly the same. The math is exactly the same. It's just that one, the light will pass through, and the other, the light will bounce off. But the spreading out of the different wavelengths and the interference pattern, all of that stuff still happens. And that's just because only the light hitting a surface, reasonably parallel or reasonably perpendicular to it will bounce, whereas the light hitting these other surfaces won't. So this kind of acts like it'll let some light through, but the next light not, and then the next light through. So it's very similar to having openings that are all next to each other. And then you can see here what I was describing earlier, that the longer the wavelength, so blue light has a longer wavelength than purple light, the more distance away that each particular bump will be. So the central ones all overlap. That's part of the reason that tends to be so bright. And then farther away, so like the m equals 1, the first order bright spot, it'll slightly separate by color. So if you shine white light through one of these gratings, you can actually pick apart the different colors. And that's what a spectrometer does. Okay, so then let's give a practice example with these diffraction gratings. So the same sodium lamp we were just looking at, that's why I had to grab this problem for us. It has 1,000 slits per millimeter. And the interference pattern is viewed on a screen 1 meter behind the grating. 2 bright yellow fringes are visible, 72.88 centimeters and 73 centimeters from the central maximum. What are the wavelengths of these 2 fringes? So we can see we don't actually need to use this 1,000 slits per millimeter. It doesn't really come into play here. That's just characteristic of how bright the bright spots will be and how dark the dark spots will be, and how thin those lines will be in relation to each other. But we can go back and grab that formula for theta. So we know that, so this problem, it's a little weird, right? They tell us that 2 bright yellow fringes are visible at 2 particular positions. So we can get theta just by thinking about the geometry here. So we have a right triangle, this is theta, this is y, this is L. So we can call one theta 1 and one theta 2. We can get these 2 angles just by doing some basic trig. So we can do a tan inverse of y over L, where we could call this one y1, and then we can do the same thing to get theta 2, but just using that other distance that we can call y2 over L. And so just to clarify here, L is our 1 meter. That's how far away the screen is from the diffraction grating. And then our y1 is this 72.88 centimeters. So be sure to convert that. And our y2 is 73 centimeters. Okay, and they want the wavelengths of each of these two fringes. So we're going to get two wavelengths at the end of the day. Okay, so what we can do is we can find the angle. So for the 72.88, I get 36.085 degrees. And you'll want to keep a lot of the digits for these types of calculations just because they tend to require high precision. And this is true in reality as well as in physics problem. And then for the other angle, I get 36.129 degrees. We'll leave it there. Okay, and then we know that these are bright spots. Okay, so they say specifically these are bright yellow fringes. So for a bright spot, we have a nice condition. We know that lambda has to be d sine theta. Okay, so how do we know that? Well, if we go back to our equations up here, so the formula for theta is that d sine theta sub m is m lambda. And 1 second here. Okay, and I guess this problem is a little weird, but I think that they're just wanting us to assume that m equals 1 for both of these fringes. And this is what we would do in a spectrometer, is that we would just focus on that first order set of bright fringes. If I give you a problem on the final or a quiz, I'll specify if it's required. But I don't think we can solve this problem unless we assume that m equals 1. So that's why if we go back to these formulas, we take m equals 1, then d sine theta equals lambda. So that's what we're doing here. D sine theta equals lambda. And then how do we get that d value? Well, they don't tell us how far apart the openings are, but they do tell us there are 1,000 slits per millimeter. So 1,000 slits per millimeter, how far apart would those slits have to be if they're all equally spaced, which is an assumption we make for all diffraction gratings? Well, they would have to be 1 over 1,000. And that's 1 over 1,000 millimeters. So at the end of the day, d would be 1 micrometer, so 10 to the minus 6 meters. Right, so we're inverting the number of slits per millimeter. That's 1,000 per millimeter. And then we're just converting that into a more appropriate unit, right? So 1/1000th of a millimeter is a micrometer. Okay, so now we can find our lambda 1 by just doing this d, which is 1 micrometer, times sine of theta 1. And similarly, we can find lambda 2 by doing d sine of theta 2. And I just happened to write these down earlier in terms of degrees, but you could do this all in terms of radians. That's honestly what I would tend to recommend, just because in other things, like in the double slit equations, we're assuming that those theta values are in radians. So anyways, I get 589.0 nanometers for the first one. And then I get 589 89.6 nanometers for the second one. So you can see these are very similar wavelengths. But that's the beauty of diffraction gratings, is that by having lots of these openings, we make the bright spots very, very narrow. So we can actually tell the difference between a 72.88 bright spot and a 73 centimeter bright spot. So that's a small distance, but you can measure it with, some computer software, taking a picture and measuring the pixels, or with a micrometer or some device. And that lets us tell apart these very, very similar colors. So when we go back up here, you can see that actually, so these two are at 589 and 589.6. So what that's telling you is that this yellow line is actually secretly two lines. So when they show us this picture, they just show one yellowish spot. But if we zoomed into that, and this is really true, there are two lines right next to each other. And so if you're an atomic physicist or some type of chemist, we call this a doublet, since there are two. And so the sodium yellow doublet, which actually comes from transitions from the d orbitals, so some people call it the d doublet, is the reason that sodium lamps look so bright and yellow. So it's kind of cool that we can tell apart these very, very close together colors. We can make super accurate measurements below like a tenth of nanometers by using these diffraction gratings. And that's kind of their usefulness, the reason that you can go on AliExpress and buy them, right? You can see we could even have bought that exact one used in the problem with 1,000 lines per millimeter. Okay, so that's section 18.4. It feels weird not pausing for questions. I feel like there may have been some at the moment, but feel free to email me if you have some come up or to rewatch this video. So now we'll move on to section 18.5. And this is a weird one. So in the previous two, we've assumed that those openings are really, really tiny, way smaller than the wavelength. And so all of the interference just comes from the fact that each of those openings has a little circular wave emanating from it after the light passes through, and those circular waves interfere with one another and create these bright and dark alternating patterns that we call interference patterns. In section 18.5, we're changing it up a little bit. So instead of having microscopically tiny openings, now we're going to think about openings that are similar in size to the wavelength of light, but that are big enough that their width actually matters. And so we'll start by just thinking about if we have one such opening. And so we call this a single slit. So just to hammer this home, with a double slit, oftentimes in physics books, they're actually drawn like this. We have two infinitesimally small openings that are separated by a distance, little d, and that's why we get interference. With a single slit, sorry, let me draw this a little bit better. With a single slit, we have one opening that has a width that we could call d. I think in the book they call it w, maybe, or no, I'm mixing these up. I think in the book they do call it d, but we'll see momentarily. So it's one opening, and it turns out that even just thinking about the wave fronts coming through the single opening, you still get an interference pattern. It's very weak, but you still will see one. And this can be really useful for measuring very tiny openings. So there are lots of tiny openings in the body. So you can take a cadaver or something, I guess, and cut someone open, get that tiny opening. And if you want to measure how big it is, if it's really, really tiny, you can shine a laser through it. It'll make a little pattern of bright and dark spots, just very similar to the double slit and the diffraction grating. And you can measure the spacing between them, just like we were doing, to find how big that tiny opening is. So this is actually something medical, like PhD scientists do to characterize different portions of the human body. It's a very powerful technique. It turns out there's a very nice principle in optics, which is that if you have an opening that causes some diffraction pattern, that you'll actually get the same diffraction pattern. So this is equivalent to if you had an opening on either side and then a solid object and then another big opening. So here, the openings on the left and right are arbitrarily big, but this little object in the way has that same size d. These two are equal. So we can also use the single slit equations to measure the width of a human hair, which is really cool, or even smaller things that are similar in scale to the wavelength of light. And if we have one thing that we can't measure, we can just make the wavelength of light shorter and we can measure smaller things. So that's something that we'll talk about more later. But you can even measure things down to the scale of molecular structures, crystals, bonds, by using shorter and shorter wavelengths, which corresponds to something like X-rays. Okay, so how does this even work? Why do we even see an interference pattern with a single slit? You would really expect not to. You would, maybe if you're thinking about throwing baseballs, you would just expect them to go straight through. And if you're thinking a little bit more deeply about a wave, you would expect it to kind of spread out, but not to really interfere. But there's an important principle that helps us understand the single slit, which is known as Huygens principle. And the idea is that if you have a wave, the way that, so we think of waves as being just sinusoidal, traveling nicely. We call those plane waves if it's just traveling in a straight line sinusoidally. But in reality, each little point on a wave is as if we had a tiny, tiny opening. So when we had the double slit, we had a tiny, tiny opening and the waves would come out of it and be circular. So Huygens principle says that even for a wave where there are no openings, we can imagine what if I had infinite openings or something like that are all tiny. And so by this analogy, we see that each point on the wavefront, so the wavefront is just the name for that, the waves that as it's traveling, that each point is like its own emitter of circular waves. And that for larger scales, we tend to be able to ignore this, that the interference between the wavefronts kind of cancels out. It's not very noticeable. And so we don't have to think about it. But if we have a small opening similar to the wavelength, which is what a single slit is, then we actually have to care about it. So you can see this is an example. We have a single slit with width A. Okay, they use the letter lowercase a here, I suppose. And we can think about each little point along this opening as being its own circular wave emitter. And so we get interference happening, right? You can see that at some places, the two lines will be crossing. That will be constructive interference. And at other places, we have a line crossing the gap between two, and that would be destructive. That would be a dark spot. And there's a whole explanation in the book on how we can take that and go from Huygens' principle to the equations that we will see momentarily. I don't want to dig too much into it, but basically what happens is we can think of the light at the top of the opening as being matched with the light right below the middle of the opening. And there are a bunch of pairs like this. So the next one would be this light and this light. So you can see 1 and 2 match up, 3 and 4 match up, and then 5 and 6 also match up. So we break the light traveling through this opening into pairs, and we think about the interference between each pair. And it turns out when we do that, one of the lights will travel a little bit farther. They label one here, this delta R 1, 2 is how much farther ray 2 travels compared to wave 1. And we can just use that interference formula from chapter 17. The whole delta phi is 2 pi delta x over lambda. It all keeps going back to that formula, basically, all of chapter 18. We can think about this delta R 1, 2 as our delta x, and we can ask, do we get constructive or destructive interference? And because of some nice symmetries, if one pair has that happen, if pair 1 and 2 has that happen, the same thing will happen for pair 3 and 4 and pair 5 and 6. It's just a very nice symmetrical geometry problem. So the book gets into it in more detail. I'm just going to skip it. You don't really need to understand how this happens at that level. You should just recognize that if we have a very small single slit with width A, which is similar to the size of the wavelength of the wave that's traveling through it, that will get some interference pattern. And so when in this drawing, the parts where it's larger, those are bright spots. And then the parts like here where it says P1, that would be a dark spot. So that's where we're getting destructive interference. And again, we have a bright spot, constructive, dark spot, destructive. You see it looks very similar to the double slit case, except here the central one is much bigger and then the other ones get smaller pretty quick. So single slit interference something you should know intuitively about it is that it's a much weaker effect than a double slit. And that in general, the interference pattern you see, so the bright and dark spots that you see, the center one will be very bright and the other ones will be very tiny, kind of hard to notice. So just to show you a picture, this is what it would look like in reality with a very small width single slit. You see the center one's very bright, so that's just the light going through it directly. But that on either side, we do get some little bits where there are constructive or destructive interference. It turns out finding the locations of the constructive bits is kind of hard, so we actually won't require you to find them in this class. But what we will require you to find are the positions of the dark fringes, sorry. So you can see both of these formulas are for the position of the dark fringes, and it's actually the same formula as for a double slit. It just so happens, but instead of using the gap between the two openings for the double slit that we call D, we've replaced it with this letter A, which is the width of the slit. So for a double slit, remember our formula for theta was M lambda over D, and this was for the bright spots for a double slit. And so for a single slit, to find not the bright spots, but the opposite, the dark spots, we use basically the same formula. P is some integer, lambda is the wavelength, and A is the width of the slit. And since this is finding the dark spots, P cannot be 0, because if P were 0, that would line up with the middle, and we can see here that there's a bright spot there. So P has to be 1, 2, 3, something bigger like that. So if we wanted to find the second dark spot, we would just say that it occurs at an angle given by the formula P, which would be 2 for the second bright spot, times lambda over the width of that slit, width of that opening. And then we can use the small angle approximation to convert that into a height. So if we wanted to find the height of the second dark spot, so that would be from here up to this P equals 2. So this would be our y sub 2, and we would just say that this is given by the formula 2 lambda L over A, where again, L is that distance from the slit to the screen, and A is the width of the slit. Okay, so the important thing is it's very similar to a double slit, but this is the positions of the dark spots, not the bright spots. So that's an easy thing to make a mistake on. It takes some practice. But we can say one fact about the bright spots. So you can see we know the position of the first dark spot. We know the position of the dark spot below that. So this one is up a distance, lambda L over A. This one's down a distance, lambda L over A. So the width of that central bright spot, so the distance right here, this is what we call W, is 2 lambda L over A. You can see that what's happening is if we look at our interference pattern, that if this is the center, so this is y equals 0, that our formulas tell us that this happens at lambda L over A, and that this bright spot, this dark spot over here happens at lambda L over A. So we could just say, well, how far is it from the dark spot to the left and the dark spot to the right? Well, it's just 2 lambda L over A, and we call that the width of the central bright spot. So the reason we like this formula, it's a little bit nicer, is that that's just the easiest thing to measure, usually. So if you shine light through a very small opening, or past, if we shine light over a human hair, it'll make a little pattern, bright spot, dark, bright, dark, and the same on the other side. And by measuring how wide that central bright spot is, that'll be our W. And you can see that it'll actually, if we know how far from the hair to where we're projecting, like on a wall, and we know how what color that wavelength is, we can actually calculate the width of the hair. You can actually do this at home. I tested it out, and it's in one of the final project topics if you decided to do that one. And you can do it with just a laser pointer and a dark room, tape the hair in a piece of cardboard like this. You can easily measure its width using single slit interference. Okay, so we have in fact, we have that exact problem here. I forgot that I included it. So student is doing a lab experiment in which she uses diffraction to measure the width of a shaft of her hair. She shines a laser, so green laser, so around 530 nanometers, on a single hair, which produces a diffraction pattern on a screen 1.2 meters away. So our L is 1.2 meters. And the width of the central maximum is 14 millimeters. So you can see that's a small distance, but it's something that you can measure with, a very accurate ruler or with some micrometers. So compare that to trying to measure the width of a single strand of hair, and you'll find that it's almost impossible. Okay, so the first question is, what's the thickness of the hair? So we had our formula that W is 2 lambda L over A. And so they want the thickness, which is effectively the width of that small single slit. So that's A, which is 2 lambda L over W, by doing a little bit of algebra. And plugging in, I got 91 micrometers. So quite small, right? That's around 1/10 of a millimeter. So that would be much, much harder to measure than measuring that width of the diffraction central max, which is 14 millimeters. Okay. And then they also ask, if she chose a wider shaft of hair, how would this change the width of the central maximum? So for that, we can look back at this formula, and you can see if the hair were wider, that would actually cause the width to get smaller. This is a very strange feeling. So of course, at a certain point, if we made the width wider and wider and wider, eventually it wouldn't follow our assumptions from earlier that the width of the hair was similar to or the thickness of the hair is similar to the size of the wavelength. So if we kept making it bigger, eventually we would be in a region where we would just use ray optics. We would say that whatever the opening size is, that's how big. So A would just equal W eventually. But it turns out, as long as diffraction is happening, if we make A bigger, if we make the hair thicker, that actually concentrates the light a little bit. And it's hard to explain why this happens other than to say we have to just follow the math, and the math shows us where we get the dark spots occurring. And so those dark spots tell you how wide the central maximum is. Of course, this whole interference pattern shrinks, so more of it is just in the range of the beam. But we could say eventually that just gets packed in enough that we just see one bright spot, and that's what would happen with ray optics. But when you're thinking about wave optics, so where the thickness of the hair is reasonably close to the wavelength of the light, or alternatively where the size of the opening is reasonably close to the wavelength of light, by making it thicker hair, or by making it a bigger single slit, we actually make that central width smaller. So very counterintuitive, I think. I remember being blown away when I first learned about this. Okay. And so the cool thing is that means it's actually easier to measure smaller things than it is bigger things when we're thinking about it in terms of single slit interference patterns. Okay, so we've talked about slits. So far, this has all been sort of thinking about them in one dimension. So if we go back to our first picture, with the double slits, you see how these lines they're lines. So it's an opening that you can make by cutting it. But in reality, oftentimes, we're more interested in circles. So for example, if I take a hole punch and punch a circle instead of cutting a line, that would be an example of what's known as a circular aperture. So an aperture is just a name for an opening. You may have heard it in the context of cameras. And so a camera also has a circular aperture. The human eye is also a circular aperture. Telescopes, microscopes, you can start to see why we care so much about circular apertures. And it turns out that circular apertures, if the opening is similar to the wavelength of light, they also make an interference pattern, which sometimes people call diffraction patterns. This language can be a bit confusing, but the waves coming through, similar to the single slit, interfere with one another in a complex way. And so we get basically the same pattern. We get the same single slit pattern. It's just, if you imagine taking that pattern and rotating it around in a circle. And so instead of these spots like, bright, dark, those happen at different radii. And so we get something like the Target logo, right? We have a central bright spot, and then we have this dark ring that corresponds to the first dark spot. And we have the next one, so on and so forth. The only thing you really need to know for this, well, there are two things, but the main thing you should know is that the first dark spot, so the location, the angle from the center to, so the angle that would cause this first dark spot, we call theta 1, it's also labeled in this picture, corresponds to 1.22 times lambda over d. And you can ask me, where does this 1.22 come from? And the answer actually goes back to Fourier transform, so it's too advanced for this class, unfortunately. But just take my word, if you do a hard integral, you get theta 1, the location of the first dark ring, angularly speaking, is 1.22 lambda over d. And this is a really important equation for any sort of optical instrument, because it basically tells us how well can we observe something. So how high of a resolution do we really have? Okay, so you can imagine, if you've ever taken pictures with your phone camera, that you can take a picture and you can zoom in and zoom in and zoom in, and your phone will just let you keep zooming in, for a long time. But at a certain point, it'll get kind of blurry. And so the point at which it gets blurry is actually it's characterized by this angle. Okay, so the other formula you should know, there are only two for the circular aperture, is that we can also find the width here. And it's very similar to this width formula in the single slit case, but instead of a 2, you can see we have a 2.44. And instead of the A, the width of that single slit, we have D, which is the diameter. It's effectively the width, right? It's how big that opening is. And so the 2.44 is just double 1.22, right? It's 1.22 lambda over d to get to the dark spot. And so to find the width of that central circle, that is based on just doubling that length. And by multiplying by L, we're assuming a small angle, but that converts the angle to width at physical distance. So this gives you a way to we can do a few things with this. We can, like I said, we can characterize when we can tell things apart, but we can also solve for one of these variables if we can measure the other three. And just as in the case of the single slit, where if we have an opening, it actually produces the same interference pattern as if we have a solid object. So hair makes the same interference pattern as having a thin slit. We can have a circular opening, and that'll make the same pattern as a solid circle. And so a really, really fun application of this that I remember doing when I was a little kid is that you can take some blood and shine a laser through it, and you'll actually get this exact same interference pattern. And that's because red blood cells are circles, basically. And so when the light shines past them, the D in the formula is the diameter of the red blood cells. So you can actually measure the diameter of red blood cells using interference patterns just with stuff you have around your house. It's really a powerful technique. Okay, so I just wanted to show you this picture. We'll come back to this in chapter 20, but to understand why the location of this dark spot, why that corresponds to how good of a resolution we can have in an image, you can see that if we have two bright objects, so two openings that are next to each other. So we can imagine this as you're looking up in the sky and you see two stars. If the stars are far enough away, then those two patterns don't overlap at all. And so we can tell that there are two stars. If they get a little bit closer, it's a little hard to tell. So that's picture B, but we can still kind of tell. And so picture B is what happens when one of these interference patterns, where the peak of it lines up with the dark spot of the next one. So this is basically as close as they can get where we can tell that it's two separate things. But then if we let them get any closer, you can see that the sum of the two interference patterns gives us just what looks like one big one. So we would just see that as one star or one object. So when astronomers look out in the night sky, oftentimes stars form in pairs. That's actually more common than our solar system where we just have one. It's sometimes hard to tell that there are two stars if they're too close. And that this is really a function of the circular aperture interference pattern, right? That characteristic width. And so that's why this theta 1.22 lambda over d, it'll show up all the time if you're reading optics papers or books, or if you're trying to figure out how small of a thing can I look at with my microscope, or how small of a thing can I image with my ultrasound. If you're doing that project, it's all related to this idea of circular aperture interference patterns. Okay, so we're almost done here. I know I would be almost going over time in the classroom, but we're just going to finish this up in one nice lecture. So the last section in chapter 18 is section 18.7, which is about X-rays and also X-ray diffraction. So X-rays, the normal pictures we take, actually don't really use the wave properties of X-rays. They're really thinking of X-rays as just a ray. So we'll talk more about rays in chapter 19, but basically they're just imagining that the X-rays go straight. There's no funny business. So if you put your hand in front of a piece of film and you shine X-rays on your hand, the X-rays will pass through and be able to activate the film in those regions, but they can't pass through your bones, so they don't activate that film. And the X-ray pictures that physicians use are actually the negatives, so they're the flipped version of that. So where the X-rays don't go through, they look white, and where the X-rays do go to the film, they look dark. And so there's no funny business, there's no diffraction happening in the context of normal X-ray imaging when we're thinking about the scale of human bones, because the wavelength of X-rays are usually like nanometer or smaller. So we can treat them very well as rays when we're thinking about X-ray imaging. And I just wanted to highlight here that X-rays are really, the generation of X-rays is really not a hard thing to do. So it's something you can learn about in Physics 3C, that basically we're just accelerating electrons in a little vacuum tube so that they don't bump into other stuff, and then making them hit really hard into a piece of metal, and that'll produce a bunch of X-rays. And so I just threw an image up here. It's something very easy to do at home, but of course be careful. X-rays are an ionizing form of radiation. So if you allow too many of them to hit your body over some period of time, they can disrupt cellular function, knock atoms out of molecules, and in particular, they can disrupt important molecules like your DNA, which is what gives rise to cancer. Okay. But what if we do want to have diffraction with X-rays? Well, since X-rays have such a small wavelength, in order to have some opening that's similar in size to that wavelength, we have to go to the molecular scale. So X-rays are actually able to tell us something about crystals, molecules, these really tiny spacings, because they have such high energy. And so you might wonder, well, Cannon, I know that gamma rays have an even smaller wavelength. Why don't we use those? And the problem with gamma rays is they just break things. So if you have gamma rays, they do have a smaller wavelength, but they'll just break they'll break your material, break your stuff. So, and they're also more dangerous. So practically speaking, historically speaking, and even to this day, we use X-ray diffraction in order to tell what molecules look like, what shape they are, and also what the crystals look like. And so as a very basic example, you can see that the X-ray, when we shine X-rays through a cubic crystal, so a crystal made up of little cubes of molecules, that it looks very similar to a diffraction grating. So as the X-rays bounce off, they have to travel some extra little distance. And the way the book chooses its angle is a little weird. It chooses an angle from the normal line to the ray. And when we do that, we get that the delta R is 2D cosine theta. If they'd chosen the other angle, which many people do, it would be a sine theta instead of a cosine theta. But in any case, the difference in the distance that one ray travels versus another will be basically this 2D and then either sine or cosine theta, depending on how you define the angle. And you can see the reason that's happening is, so this is one ray here, and then this is the other ray, and you can see it travels this distance, which matches the other one, but it also travels this extra little bit. So there's a d cos theta here, and there's a d cos theta here. So the overall difference in travel path is 2d cosine theta. And so we know that if we have that travel path, that extra distance, as an integer of the wavelength, that will have a bright spot, constructive interference. And so we just, it's really all coming from that delta phi is 2 pi delta x over lambda. All this stuff in chapter 18 is just different ways of applying that equation. So we apply it yet again, and we have 2d cos theta equals m lambda. And so this is known as the Bragg condition, named after a famous X-ray physicist, which gives the angles for which we have constructive interference for X-rays reflected from a solid, assuming that there's like a cubic crystal structure. So making some assumptions that this is sort of a more basic condition. We can have more advanced ones depending on the type of crystal. But this is the only one you really need for this class. And you can see here that that theta, just to highlight it, is the angle from the normal to the ray. So if this is my surface, let's say I have some metal here, and I shine X-rays on it, like this. If I shine them at this angle theta, let's say that I have a bright spot, but if I shine them at a different angle down here, then they would bounce over here. So if I shine them at this bigger angle, maybe I have a dark spot here. You can kind of see how this works. So what I do is I take my material, I clamp it down, have a flat surface, and then I shine my X-rays. I start here, and I get bigger and bigger thetas. It's going to bounce off at that same angle. But some of those reflected rays, sometimes it'll be bright, and sometimes it'll be dark, depending on where I'm at in the interference pattern. So that's how it works. It's a little different than the other cases, but it's a very similar formula. So we can do an example problem here. So we have X-rays with a wavelength. You can see the typical X-ray wavelength, very, very small, of 0.105 nanometers. So 100 times smaller than visible light. They're diffracted by a crystal with a simple cubic lattice. Good. That means we can use our Bragg condition. And we see maxima occur at angles 31.6 degrees and 55.4 degrees, and no angles between these two. So we can convert these to radians if your calculator is in radians mode, or we can just evaluate them in degree mode directly. So we have some theta. Let's call this, let me pull up my calculation notes here. So some theta that we can call theta m plus 1, which is 31.6 degrees. And some theta m, which is 55.4 degrees. Okay, and you might be wondering, okay, Cannon, why did you call these m plus 1 and m? Well, they say that there are no angles between these two where we get maxima. So we know that these are adjacent maxima in the interference pattern. So one will be some number m, the other will be some number m plus 1. Okay. And so then you have to ask yourself, how do I order them? Which one is the m and which one is the m plus 1? And so we can go back to our formula, and we see we have a cosine here. So if we have a bigger m, so that means the right side is bigger, then we need the left side to be bigger as well. But for cosine to be bigger, it needs to be, the angle needs to be closer to 0. So for everything else held constant, the lambda and d held constant, a smaller angle will be a bigger m. This is a really weird thing about how they define the angle. This is why I think the book is a little wonky here. But I want you to be able to match their notation. So if they ask you for an angle in homework, that you can calculate the angle they want. Right, so this is, remember, this is the normal angle. So the angle from a line perpendicular to the surface to where the beam is. Okay, so that's why we call 31.6 degrees theta m plus 1 and 55.4 degrees theta m. And now we don't know anything else about this problem really, but we do know, you can see, we know this Bragg condition. We know that 2d cosine theta m equals n lambda. And since everything in this formula, the d and the lambda are going to be the same for both of these situations, we can make this into sort of a proportionality condition. So we know that 2d over lambda equals m over cosine theta m. So that was just from rearranging the equation. And since the d and the lambda are the same for both angles in this problem, what we can say is that m over cosine of theta m, which is the 55.4 degrees, equals m plus 1 over the cosine of theta m plus 1, which is 31.6 degrees. And we can evaluate this expression and solve for m. And when I did that, I encourage you to try it out as well. I got m equals to 2. So that tells us that this 55.4, this is theta sub 2, and this 31.6 is theta sub 3. And so now, in order to get the spacing between the atomic planes, so this is the d value, we just have to use one of the two angles and solve the Bragg condition for that little d variable. So just getting that little d on its own, the formula is m lambda over 2 cosine theta m. And then let's just use, I don't know, the theta sub 2. So this would be, our m is 2 times lambda over 2 times cosine of theta 2, which is the 55.4. You see, we could have also done it with m being equal to 3. We just would have had to take cosine of 31.6 instead. And I encourage you to try this in your calculator yourself, but when I evaluate it, I get 0.185 nanometers, which remember, an angstrom is just a tenth of a nanometer. So this is 1.85 angstrom. Angstrom isn't a metric unit, so you don't need to know how to convert into it for this class, or if you do, I'll give you the conversion in the problem. But it's a typical unit used for atomic sized things. So this is telling us that the spacing in this atomic lattice, so between the molecules, is almost 2 angstrom, which is very reasonable. That's very typical. But you can see that with X-rays, we can measure really tiny things, right? This is something that we can't see. You couldn't even see this with a microscope, right? You would have to have a special type of microscope, an electron microscope, to see something this small. But this is quite a big difference in angle, right? 30-degree angle versus 50-degree angle. That's something that humans can measure. That's something very visible. And so by using X-rays and the fact that they have an interference pattern with one another, that they diffract, we can measure these really tiny quantities. And so to give you one example of where this comes up, so in biology, of course, we have much more complex angles because we have much more complex molecules. So when you're dealing with something like an enzyme, the molecular structure won't be a simple cube. So we can't use the Bragg condition quite so simply. It'll be a bunch of cubes all mixed-mashed and mished together. So we'll get a bunch of different angles where we get constructive interference. And so this picture here, you can see the bright and the dark spots for some enzyme. This line is just based on limitations of the measurement. So this line isn't actually part of the interference pattern, but these dark spots are actually telling you in a very convoluted way what the molecular structure looks like and what the spacing is between the molecules. And so for this particular enzyme, I don't know exactly how to interpret this, but there's a whole field of study where all people do is get these weird pictures and find ways to interpret them. And that's actually how we know so much about what molecules look like, and especially biological molecules that are very complex. But one really important example is DNA, right? So this diffraction pattern on the left, or interference pattern, again, we use both names for such things, is what Rosalind Franklin found for DNA. So it's by taking a sample of DNA and bombarding it with X-rays at different angles and projecting that onto some film and seeing where are there bright spots, where are there dark spots, we actually get this beautiful image. And by interpreting this image correctly, this is how historically people, particularly Rosalind Franklin, although of course others have gotten credit, we're able to discover what DNA looks like. And not only what does it look like, but how big is it, right? How big is the spacing between the base pairs? How big is that the angle of the twist? All of that information is contained in a very convoluted way in this diffraction pattern. And it all starts with things like this Bragg condition. So this Bragg condition is the fundamental basis of interpreting images like these. Okay, so hopefully that gets you excited about physics. And I'll leave it there. That's the end of chapter 18. We'll start back up on Tuesday with chapter 19, which is all about ray optics. So things like mirrors and lenses and whatnot. So if you're doing the homework, you may want to look ahead, but I'll dig into all that detail on Tuesday. So best of luck. Make sure you're turning things in, the projects and the homeworks and whatnot that are all coming due soon. And I'll see you after the holiday.